So in this video we're going to go over an example of using the arc length formula to calculate the length of an arc in polar form. So it says calculate the arc length of r equals 2 plus 2 sine theta of this cardioid. I think this is a cardioid. I think in the previous video I was accidentally calling this a limicon. But a limicon is the one where it sweeps through like this. This is a limicon. And then this is a cardioid. So now I'm going to have to redo that whole video, but I'm not going to redo it tonight. So I just have to live with that mistake and eat crow. So it says calculate the arc length of the cardioid given by radius equals 2 plus 2 sine theta over the interval from 0 to 2 pi. So I think it's a good thing to figure out what arc length it is you're trying to find. So if you plug 0 in here, you get 2 plus 2 times the sine of 0 is 2 plus 2 times 0 is just 2. So when you're in the 0 radian position, you get a radius of 2 and an angle of 0 radians. Remember, we're working in polar form, so our ordered pairs are radius comma theta that generates that radius. And if we plug pi over 2 in, we're going to get sine of pi over 2 is 1 times 2 is 2 plus 2 is 4. So when we're at a radius of 4, we have an angle of pi over 2. So the radial line is right here. So we're just calculating the arc length as we sweep through the angle from 0 to pi over 2. So we're essentially calculating the length of the arc of the cardioid in quadrant 1. That's all we're being asked to find. And then we know that the arc length formula says, hey, to calculate the length of the arc, just take the integral from 0 to pi over 2, and then our arc length formula from the previous slide, we just have to do the sum of the squares of the radius and the derivative of the radius. That was the formula that we just developed. So this is going to be the square root of, we need r squared plus r prime squared. And this calculation here, and this is going to be d theta. So this calculation here is a little bit messy. So we probably want to work it through off to the side. So we know r is equal to 2 plus 2 sine of theta. So when we square r, we're going to be squaring this. So we'll get 2 times 2 is 4 plus 2 times 2 twice. 2 times 2 sine theta twice. We'll get 2 times 2 is 4 times 2 is 8 sine theta. We'll get plus 8 sine theta plus 2 times sine theta times itself. So we get plus 4 sine squared theta plus 4 sine squared theta. And then we're going to need to find the derivative. So r prime. And r prime is just going to be 2 times the cosine of theta. And we know we need to square that, which will just give us 4 times the cosine squared of theta. And then we need to take the sum of these two squares. So when we do r squared plus r prime squared, we're going to get 4 plus 8 sine theta. This is going to add up to 4 plus 8 sine theta. Then we're going to get 4 sine squared of theta plus 4 sine squared of theta plus 4 cosine squared of theta. What we want to notice about that is that the 4 shows up in each term, so what we can actually do is factor the 4 off, and that's going to leave behind a sine squared of theta plus cosine squared of theta. But we know that by the Pythagorean identity that's equal to 1, so we wind up just getting 4 when we add these two pieces right here together. We're adding r squared plus r prime squared. So we get 4 sine squared plus 4 cosine squared is 4, and 4 plus 4 is just going to be 8. So we wind up, when we add the sum of these two squares, we get 8 plus 8 sine theta. We can factor an 8 off. We get 8 times 1 plus the sine of theta, and 8 is really just 1 plus the sine of theta, and 8 is really just 4 times 2. So this is the mess that's going to go underneath the radical sign. That's just doing some scratch work. So this equals We'll take the integral from 0 to pi over 2. We'll do the square root of, and it's going to be 4 times 2 times 1 plus the sine of theta d theta. And I'm going to erase my scratch work here to give myself a little room down here. So this is a scratch work piece. You wouldn't want to have to drag that integral along with you. And here what we want to recognize is this will clean up a little bit because the square root of 4 is 2 and the square root of 2 is just the square root of 2. So we can get the constant out front. We're still going from 0 to pi over 2, and this is the square root of 1 plus the sine of theta. And a tip on these, something that you want to be looking for when you're doing the homework, it's nice when you can get a 1 plus a cosine or 1 minus a cosine in here, which we were unlucky and didn't get, because we would have gotten it. Had I put a cosine here instead, I think we would have gotten that in here, but I didn't, so we're getting the 1 plus a sine. But you do want to watch for 1 plus or 1 minus the cosine under the square root, and let me show you why real quickly. Let me escape this and keep those so we can add on to them. So when you're thinking about trigonometric identities, if you can get a 1 minus a cosine right here, or 1 plus a cosine, then if you square both sides of the half angle identities, you can dig that 1 minus the cosine or 1 plus the cosine out, and you can rewrite it in terms of a sine squared or a cosine squared. And so then you'd be taking the square root of a sine squared or a cosine squared, which would simplify very nicely. So when you see a 1 minus the cosine and 1 plus the cosine sitting under the square root, you want to think about how you can use the half angle identity to make your life easier. Here, this one, I didn't intend on doing this one through, but I think we want to push this. I was going to go dot dot dot, finish the integral. But this one is a sneaky little sucker. There's more than one way to get at him, but he's kind of yucky, and so I think it's worth just pushing him a little bit further. So the trick in finger quotes, one way to deal with this is to multiply this by a funky form of 1. So you do 1 minus the sine of theta, the square root of 1 minus the sine of theta over the square root of 1 minus the sine of theta. And then that gives you a square root of 1 minus the sine of theta in the denominator. And then these two, you bring them under the same square root and you multiply them out, which is going to give you, this is a difference of squares form, right? When we have a minus b times a plus b, we get a squared minus b squared. So this would give you, if you brought them both under the same radical, so you say, hey, they can be brought under the same radical like this, then you get a 1 squared minus sine squared, which by the Pythagorean identity is the same as the cosine squared. So you wind up with the square, if you multiply by this, here's what you wind up with, 1 minus the sine of theta. And then you can kind of see where this trick could come into play. If you started with a 1 minus the sine, you would do a 1 plus here and see if anything good came out of it. So if you wound up, let's get them written back in here, dang it, 1 plus the sine of theta. If you, and d theta, if you multiply this guy out and do some simplifying, so some simplification work, you get 2 root 2 from 0 to pi over 2, and you wind up with the cosine of theta over the square root of 1 minus the sine of theta, which doesn't look good initially. This is d theta, but you make the substitution. Here you make a u substitution. You say let u equal the square root of 1 minus the sine of the theta. And then you do du d theta, so we get du equals, and here you get 1/2 times 1 minus the sine of theta to the negative 1/2, which is the same as writing it down in the denominator position. So du equals 1 over, we get 2 times the square root of 1 minus the sine of theta. And then the chain rule says you have to take the derivative of the inside. So the derivative of that's going to be minus the cosine. So you get minus the cosine of theta. And this is all going to be, if this is du d theta, then over here we wind up with the d theta. And then if we multiply both sides by -2, so we do negative 2, we get -2 du. The negatives comes off of here. My pen is starting to act up on me. So we can replace cosine d theta over square root of 1 minus sine of theta with -2 du. We can make that substitution, and then it becomes easy to integrate. So at that point you can kind of dot it. You wind up with, I'm going to use really bad form here. You wind up with -4 square root of 2 integral, and then this is going to be just du. And then you have two choices. You either change the limits of integration, you plug 0 in here, and you get sine of 0, 0. 1 minus 0 is 1. Square root of 1 is 1. You change the limit of integration there to 1. And then you plug in the pi over 2. You get sine of pi over 2 is 1. 1 minus 1 is 0. Square root of 0 is 0. And then if you reverse the direction to get the larger number on top, if you change this from 0 to 1, what that does is negates the integral. You get negative, negative is positive. So you get the integral from 0 to 1 of 4 root 2 du, which just equals 4 square root of 2 times u from 0 to 1 is just 4 times the square root of 2.